take a look and try to make connections, which I think we've already made before. So I'm feeling good about the connections that we're going to make. Let's see. Let's grab these guys. Here we have the graph of a function, graph of its derivative. And let's see. Okay. And we're going to ask some questions about it. And hopefully these questions will at least make sense. And if not, maybe we can ask some questions to help clarify. All right. Let's see. I need to turn that off. Uh-oh. Uh-oh. Oh, there we go. Okay. All right. That works. And now we want to do... All right. Yeah. You don't have classwork? That can't be true. I don't believe you. So it's part of the classwork packet. Oh, there's your problem. I'll get it for you. Probably it's not going to be right now. How have you been getting along for the last 3 days, 4 days?
I just take notes in my...
Good for you. Way to be. That's nice. All right. So let's take a look. Let's see if I can do this. It's not what promising. Oh, no. Yep. Hey, what are you doing? Yeah, send that down.
Thank you.
All right. So we're going to look at the graph of the function and the derivative. So part A says, for what value of x is the function increasing? All right. I'd actually say there are a couple intervals that you could tell me. So, Rachel, you want to start me with an interval where the function is increasing?
First graph.
I don't know. Which one's the function? Okay. So tell me the first one.
Between 0 and 1.5.
Okay, so around there. Do you agree with Rachel?
Yes.
Okay. Rachel, call on someone to tell me where else the function is increasing.
Between 5 and 7.
Is that as good as you can do? Okay.
From the valley.
All right, so give me a value.
4.5.
Okay. Up to about... All right, no one's going to argue with you. You called it. We agree. Way to go, Morgan. All right. So the question says, what's the behavior of the derivative on those intervals? So Rachel said 0 to 1.5, and Morgan said, 0 to 1.5 is what you said. And then Rachel said, no, that's what Rachel said. And Morgan said around 4.5 to 7.5. So we know that the function's increasing. Arnie, what can you tell us about the derivative on those intervals? Try again.
Well, it's increasing.
Yeah, that's not a helpful observation, huh? Try again. I think you can do it. You tell me. Is it positive? What does positive mean? No. What's positive mean? Julia, what's positive mean? Just answer that question. All right, so Arnie, is it positive? Is it above the x-axis? Yeah. Definitely, without a doubt. Okay, so the derivative is positive. What's another name for derivative? Slope. Does it make sense if the slope is positive, the function is increasing? Yeah, okay. So I'm going to write our first observation. If the function is increasing, it's actually a two-way arrow, the derivative is positive. Does that observation make sense conceptually? I think it does. And it actually makes sense with this picture too, but I think that makes sense conceptually. All right, let's turn it around now. Sam, For what values is the derivative negative?
Between 1 point, I guess it's 6,
Okay.
and 4.2.
Okay.
And also, if I say the second one,
Sure.
between 7.5 and 10.
All right. So now, David, follow up on that. The question is, what can you say about the function on those intervals? I don't think we'd say the slope is decreasing. The function's decreasing. Okay? And I've said it before and I'll say it again. You're going to get confused with the words decreasing, increasing, function, derivative. It's going to be very important. Don't use the word it. Don't say it's increasing or it's decreasing. Make sure you use the words like the function is increasing. All right? So here we note that the function is decreasing has a relationship with the derivative being negative. Is that all right? Makes sense? Drew, ask a question. You want to get a question in about that? You don't have to, but I just thought, No. You sure? Arnie, question.
No.
Oh, really? All right. Guess I'm just teaching it so well. I'm going to jump to E for a second. Where does F have minimum and maximum values? So let's look at mins and maxes. Kelly, give me some mins and maxes.
Of the function.
What does the question say?
Local minimum. I don't know. I guess the minimum would be 1-ish.
1? Right around there?
No.
Okay.
4.2.
All right, so around 4 point something, there's a minimum. Okay, now, can we discuss the word local? Because Kelly was stuck on that a little bit. Do you see that there's definitely a minimum at 4.2 or something? It might not necessarily be the minimum, though. Can you actually see maybe down here at 10 might be even less? So we call 4.2 a local minimum. In its neighborhood, it's the least. Okay? And neighborhood means like around it. It's the least. All right, let's take a look at...
So the grappling one, the 10 the
It's sort of...
is it the first minimum?
No, it's not the first. You can actually have more than one local minimum. You actually can't talk about local... Well, okay.
But I'm saying it's 1-1.
It's hard to tell. Does it go like this? Then local means in its neighborhood. So is 4 in its neighborhood the smallest? Yeah. So it stays a local minimum. What you might be alluding to, though, Alicia, is there an absolute or global minimum, a minimum that's less than any other point on the function? And we're not ready to talk about that yet, but certainly in this case, I would say 10 is less, has a smaller value than 4.5. We would actually maybe say 10 is a global or absolute minimum. But we're not doing that now. I want to know maximums now. Okay. Dan, give me a max.
Around 1.5.
Around 1.5. And go ahead.
Around 7.5.
Great. So at 1.5, at 4.2-ish, and around 7.5, what can you say about the derivative there? Go ahead, say it, Julia.
It's either changing from positive to a negative function or negative to a positive.
Yeah, and we have a pretty special name for those. What is that? What are they? Say it loud, everyone.
Zeros.
Those are the zeros of the function. That's where it changes from positive to negative or negative to positive. Those are the zeros. So in other words, it's saying the slope is 0 at the minimums or maximums. That sort of makes sense, don't you think? All right. I'm going to try C. I'm not really ready to talk totally about C yet, but I'm willing to try it today, and we'll probably come back to it in a couple days. So, let's see. Katie Rayner, can you read us C?
For what values of x is the derivative increasing?
All right, so I need to... Now, this is not a question we've asked you before, Katie. Where is the derivative increasing? Give me an interval.
Like 3 after 3
Okay.
to 6.
Okay. Calling someone else to give me 2 other smaller intervals.
From like 4 after 9 to 10.
And maybe 0 to 0.5. All right, now, C asks, what's the behavior of the function on those same intervals? What can you say about the function on these intervals? And this is actually a hard question. And once you get it, it's actually an easy question, but until you see it and get it, it's actually a very hard question. Ian, do you think you see it?
Maybe.
All right, give it a shot. I'm going to say this. There's a right answer, and I'm looking for it. And you might say something that might be correct, but not the one I'm looking for. So if I shoot you down, don't let your feelings get hurt. I still like you.
Okay. The function is concave up.
Very nice. Very, very nice. The function's concave up. It's bending upward in all of these instances. And that's absolutely true. That was a nice observation, Ian. Way to be. We might also say that when the derivative is decreasing, the function's concave down. It's frowning. All right, so if the derivative is increasing, the function is concave up. And if the derivative is decreasing, the function is concave down. And again, I'm not going to spend a lot of time focusing on that relationship today, but over the next couple of days, I think it's going to be more and more important to talk about that relationship. So we have 4 relationships that go 2 ways. So it's actually 8 relationships, right? If the function's increasing, the derivative is positive. If the derivative is positive, the function's increasing, right? It goes both ways. Do you understand how it might be confusing at some point? Like you might get yourself mixed up? You know where some of you know you're that person. Who's the person that's going to mix it up? Okay, we have one person readily admitting that she'll mix it up. Another person, great. All right, it's going to happen. You just want it to happen like on homeworks and quizzes, so that when you get to the test, you can feel confident about it. All right, we good? Get a drink, please. All right, we're going to practice drawing some derivative graphs based on everything that you just told me. All right, so I'm actually going to take a look at these graphs here, and we're going to sketch a graph of the derivative. All right. All right, the first one is actually pretty easy to draw the graph of the derivative. Derivative is another name for slope. What's the slope of this graph? What is it? I heard 1/2 and I heard 1. 1/2? 2? 1/2. Does the slope ever change? No. The slope's always 1/2, so actually the derivative function just looks like this. Y equals 1/2. Isn't that nice? It will. It'll get harder. But can you see if I actually give you a linear equation, y equals mx plus b, what's the derivative equal to? M, the slope. The derivative's constant. Does that make sense? The slope of a line is constant? Totally does. Without a doubt. What if the line was horizontal?
There is no derivative. Wait, no, my bad.
Just 0.
0?
Y equals 0.
Y equals 0. So if the line is horizontal, the slope is 0. Yeah, I think that's true. Okay. What?
No, I'm just...
Oh, yeah. All right. Let's take a look at something like this. This is a little harder, right? This is how I would approach it. I know the derivative at this maximum is what?
0.
Do you agree it's 0? And I know the derivative at this minimum is also... So I have 2 zeros that I'm going to start with. And those zeros are going to divide my graph up into zones. So I'm going to have 3 zones. Tell me, what's happening? What can you tell me about the function on the first zone? All right, so f is increasing. What about the second zone? F is decreasing. And on the third zone, f is increasing. Let's take the relationships that we know. When f is increasing, what do we know about the derivative? When f is decreasing, and, oh, well, you already told me that. So the derivative needs to go from positive. What does positive mean? Above the x-axis. To negative, below, to positive. So, I mean, you can imagine a lot of different ways of going from above to below to above, right? I don't know. I might start by actually asking, how steep is the line right here? Pretty steep? Like, is it a slope of like, what? 5, 12, 20? Like up 4 over 1 maybe? Okay. So, you're telling me that at negative 3, the slope is around 4. Is that what you said? So at negative 3, the derivative is going to start at around 4. And I'm going to be positive. I'm going to come down. I'm going to dip below the x-axis. And then I'm going to start back up. And that's my first estimate at what the derivative function looks like. Do you want to ask any questions about how I came up with that function, like other than just picking a couple points, 3 zones, and like sort of sketching it in? Dan? Drew?
So are you just, you're just kind of assuming that's where it goes? Like, you know what zeros it goes through, so you're just assuming it goes straight up?
Well, I actually know that it goes back up because if f is increasing, the derivative has to be positive. So you're saying, how do I know it's not a v, right? It could be a v. I know a little something, and I know it's a curved polynomial. You're going to make hold on to it. Are you going to tell me something or ask me something? All right, hold on to it. I know what you're going to tell me, and I'm looking forward to this. So I hope I am. I want it to be the right thing. All right. I don't want it to be like, get out of the classroom and never come back or something like that. Or I'm going to hunt you down and slash your tires after school. Like, I want you to tell me the math thing, right? Okay. So Drew says, how do I know it's a nice smooth shape? I actually know that. Another thing you might ask is, how do I know that it doesn't dip like really far below the x-axis? And I would say, that's a good question. What's the slope here about? Is that a steep slope or not so steep? So I would say if the slope there is only like a quarter or something, we should only be dipping below the x-axis a little bit. And believe me, tonight I'm just going to be happy that you do them. All right? It's going to be hard the first time. By the time we could do it the second and third time, though, those are the questions I'm going to be asking you. And you're going to be asking each other when we put them up on the board, like, oh, you know what? I really thought that it was a little steeper there. And we'll look at it and we'll be like, oh, yeah, you were right. All right, so David, this function looks something like what?
That looks like a polynomial function.
What kind of polynomial function?
No fun.
Oh, really? All right, go. Tell me what you're going to tell me then.
I was going to say you could probably turn it into an estimate of what that polynomial function is.
Okay.
And then you can find the derivative from that.
Yeah, that's a lot of work. Dan, what?
It's the actual function. The first.
Yeah, the first one.
That's a like 30 degree.
So something x cubed. David would tell us that the derivative then is going to be something
3x squared.
Something x squared, right? Depending on what the something in front of the x cubed is. Does that actually make sense? Here's a cubic, and the derivative is 1 degree less. Yeah, that actually makes a lot of sense. So if it's a polynomial, if it's like a nice curved, well-behaved function, you can actually use that rule in your mind. Like if you're looking at it and it looks like it's a 4th degree, your derivative is going to look 3rd degree. All right. Rachel, Sam, and then maybe one more practice problem. I don't know if it's going to happen.
Sine function where it's like this person where it like flips and then if you keep counting it's just into
So the sine function exhibits the same behaviors that we're discussing, but it has nothing to do with a degree less or a degree more. Like it's not a polynomial. So.
But like if you did it again to the fourth and then the derivative of each side it would like go back over it. You'd have another
Like that? Maybe. I don't know. Sam!
Is it always exactly 1 degree less?
If it's a polynomial, that's true, and I can tell you that. It is.
Can we go over the next one just like that?
Because you can't do corners.
All right. This one?
Yeah.
Okay.
Yeah.
Let's see. All right, I'll tell you what I'm going to do. So, Morgan, I'm going to tell you this. The derivative here is 0, and the derivative here is 0.
Well, actually, that wasn't my question was like, so I did the thing where like you're gonna like mark the zeros or whatever.
All right.
Like section it off, but in the one section between 0 and like 3.2 or whatever, it's like increasing and decreasing.
All right, so what would you say about the slope from -1 to 1? What's that slope? 1? All right, so I actually draw the slope at 1. What's the slope from 1 to 2?
3.
3. So my slope here is at 3, and there's actually a big jump. Because what's wrong with the function right there?
It's a corner.
It's a corner, and corners give me problems. There's no derivative at the corner. Likewise, Morgan, there's no derivative at this top. It looks like a maximum, right? But there's no derivative because it's a point. It's a corner. So this function actually, to be honest, it looks a little scary, but when we do it, it's actually nice because it's just line segments. So the slope from 2 to 4 is at -3. So I would just fill in -3, and then the only thing I have to do here is the slope of...
So you just draw those lines like that?
Is that -1/2? No, what is that? That's weird.
Aren't they all corners though? So what's the
-3 halves.
-3/2. So they are all corners, and Drew, if you look at all of those corners, there's no derivative, right? If you wanted to do this, you'd actually do a bunch of open circles.
Oh, okay.
You know what? I'm sorry I didn't draw them there. The greatest integer function or the step function?
Okay. You have
It's
to remember,
not.
like, we did
Yes.
one of the projects
I don't know if that's true.
It's not the step function, although this does have steps, but there's a specific function called a step function.